Today we're going to look at reciprocal functions and specifically how to take our knowledge of polynomial functions and translate that into the building of a reciprocal function. We're going to begin here with the function y equals x. I've got the graph of the line drawn along with a few sample points. We're now going to build a table of values for 1 over x based on these points. If I take negative 2 and I plug it into my reciprocal function 1 over x, I'll obviously get the same y value except that the y value will be the reciprocal of what it was before. So the negative 2 will become negative a half. And similarly, the new y values will be the reciprocal of the previous y values. So I'll take the reciprocal of each one of these points. When I get to 0, reciprocal of 0 will be undefined. Reciprocal of a quarter is 4, and so on. Now I'm going to plot these points and see if I can see a relationship between the original points and the new points. Starting with negative 2, negative 2, the point is no longer negative 2, negative 2. The y value is the reciprocal of what it was before. So at this point, negative 2, the y value will become negative a half. So here's my new point. For negative 1, the y value in reciprocal was negative 1. So that point stays the same. A y value of negative a half becomes a y value of negative 2. If I take some other points in the neighborhood, right where I'm pointing, y equals negative a quarter would be y value of 4. These points are dropping more and more. Y equals negative a tenth, right around there would be a y value of negative 10. The points are coming down, 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 approaching this line, the y-axis. Now why would that be? Well, you'll notice that at x equals 0, the y value is undefined. And so what is happening there, I can see from my points, is that I'm approaching a vertical asymptote. Let's just see what's happening on the left part of the graph. Let's take some more points that aren't included in our table. For example, this point with a y value of negative 3, if I reciprocaled that, that would be negative a third. A y value of negative 4 would be negative a quarter. I can see the points this time, the points that were further away when reciprocaled are getting close to the x-axis, creating a horizontal asymptote towards the x-axis. On the other side of the graph, a similar thing is happening. Picking up with our table once again, a y value of a quarter, right around there, is now a y value of 4. A y value of a half is now a y value of 2. A y value of 1 is still a y value of 1. A y value of 2 is a y value of a half. And a y value of 3 is a y value of a third. And again, I can see the vertical asymptote and the horizontal asymptote coming into play. The shape of this graph is fairly typical of many reciprocal functions. Let's just take stock now in terms of the properties that we see. On our original function, the line, the domain, was all real numbers. The range was all real numbers. The zeros of the function were x equals 0, and there were no asymptotes, so that's not applicable. Now when I created the reciprocal graph, what happened is that I had undefined points, and I had undefined points at x equals 0. So x cannot be 0 on the domain, but it can be any other real value. Now what ended up happening at x equals 0, I'll notice, was my vertical asymptote. So where it says vertical asymptote down here, we can say that that's created at x equals 0. The range of the function, from looking at it, is all values of y except this value of y. Y cannot be 0. That's my range. Y cannot be 0, but it can be anything else. And what's going on at y equals 0? From my graph, I can see that I have a horizontal asymptote. So the equation of my horizontal asymptote, y equals 0. And there were no x-intercept zeros of the function for the reciprocal function. Reciprocal functions take a little time to catch on to, so let's try another couple of examples. Y equals x minus 2, we're going to reciprocal to become y equals 1 over x minus 2. Again, we have some sample points in our table, and we know from our previous example that the y values of the reciprocal function are the reciprocal of the y values of the original function. Just to make that clear, for example, if I plug negative 1 into my reciprocal, negative 1 minus 2, here's the negative 3, but it's not negative 3, it's 1 over negative 3. So it's not this value, it's the reciprocal of that value. And similarly for each of these other y values. We will take the reciprocal of each of those. Reminder that the reciprocal of y equals 0 is undefined, y equals a half is 2, and so on. Now I'm going to graph these points. Starting on the left, let's take our point that we selected at negative 1, negative 3, right here. We know the y value reciprocals. We take the reciprocal of negative 3, that is, which is negative a third. Negative 2, negative a half. Negative 1, negative 1. X equals 0. Reciprocal is undefined, which we know typically shows up as an asymptote. And we also know that again because if we take points in the neighborhood, such as right here, y equals a half, y equals 2. A y value of a quarter, a y value of 4. The points are going down towards the asymptote. Similarly, on the left side of the graph, a y value of negative 4 is now a y value of negative a quarter. A y value of negative 5 is now a y value of negative a fifth. And the points are approaching the x-axis. On the other side of the graph, 2.5 had a y value of a half originally. Now it has a y value of 2. Half becomes 2. y1 becomes y1. Y value of 2 becomes a y value of a half. A y value of 3 becomes a y value of a third. The points approach the x-axis as a horizontal asymptote. These points approach the vertical line, x equals 2, as a vertical asymptote. Once again, we get our typical reciprocal shape as I mentioned. Not to say that all reciprocal functions look exactly like this. So my domain was x cannot be 2 because that's where the function was undefined. Those are our restricted values. X cannot be 2. What's happening at x equals 2? Well, actually, that's the vertical asymptote. So the vertical asymptote is at x equals 2. What about our range? Our range is all values of y except y can't be 0 because there's a horizontal asymptote going on there. So my range is y cannot be 0. And what's going on at y equals 0? That's the equation of the horizontal asymptote, y equals 0. So you'll notice that the domain relates to the vertical asymptote, the range relates to the horizontal asymptote. Let's now take an example where we work directly from the graph and we bypass the use of the table, now that we have the idea happening. So if we're asked to graph y equals 1 over, that's the signal that it's reciprocal, 1 over x plus 1, I'm going to graph, first of all, x plus 1 because I'm quite familiar with that. A y-intercept of 1 and a slope of 1. We graph the points, make some points clear so we can work with those in terms of building our reciprocal function. All right. So you'll notice from our last example that whenever we had a 0 of the function, a y value of 0, that became a vertical asymptote. So we can dot that in. You will also have noticed that any of the points with a y value of 1, such as this one, or a y value of negative 1, such as this one, when those y values are reciprocal, you have the same y value. In other words, these points will be unchanged. Let's take some other points. When y equals 2, y was now a half. When y was 3, y is now a third. Y is 4, a quarter. Points that are further away end up closer to the axes. Okay? What about this point right here, when y is a half? That becomes 2. Points that were close to the axes become further away. Right here, y equals a quarter, y equals 4. And again, you have the points following and approaching the x-axis as a horizontal asymptote and this line as a vertical asymptote. Similarly, on the other side of the graph, y equals negative 1 is y equals negative 1. Y equals negative a half reciprocal is y equals negative 2. Y equals negative 2 is y equals negative a half. y equals negative 3 is y equals negative a third. And the points approach those asymptotes. So my domain of my original function, I can actually tell that from the equation. X can't be negative 1. Visually on the graph, what's the meaning of this missing domain point? It's a vertical asymptote. So the equation of the vertical asymptote is x is negative 1. The range is all values of x except y is 0. So the range is every y value except 0. And what's going on at y equals 0? Well, that's the horizontal asymptote equation, y equals 0. Let's now look at an example of a quadratic function and taking the reciprocal of that. So I've selected y equals x squared minus 4, which is a standard parabola shifted 4 units down with the vertex at 0, negative 4. And we're going to build the reciprocal function. All right? So now that we've done a couple of examples, we can kind of streamline our work a bit. Essentially, it comes down to a few major things. The x-intercepts, we know, that have y values of 0 become vertical asymptote. So we dot those in. We have also noticed in previous examples that any points with y values of 1 remain the same, and y values of negative 1, these 2 points here will remain the same. Because when you reciprocal 1 or negative 1, you have the same value. Let's take some other points. A y value of negative 4 is a y value of negative a quarter. Y value of negative 3 is a y value of negative a third. A y value right here, a little hard to see, negative a half, is a y value of negative 2 on both sides. Y value of negative a tenth would be negative 10. So you have the points dropping, and as we come up here, coming up to the negative 1 quarter. So the points are going to look something like this. All right, on to this side of the graph, let's just pick some points. Let's pick this point, negative 3 is negative a third. Higher up, reciprocal to be lower down. And so my graph's going to swing up like so, and it's going to do a similar thing on the other side. Okay, y value of negative of 1 is 1, y value of a half is 2. The points are close, they hit 1, and they come down and approach the horizontal asymptote. So we get a bit of a different shape when we take the reciprocal of a nonlinear function, okay? But we get a graph with a lot of asymptotes. The domain. The domain of this function we can get by looking at our restricted values. X cannot be 2 or negative 2. And what goes on at those 2 points, at the undefined points, we have a vertical asymptote happening. So the equation is x equals 2, x equals negative 2. For the range, I pretty much always have to look at the graph to get the range. The range is more difficult to do generally than the domain. All values of y are being used for this graph, except a few of the points around here. So y equals 0 is not being used, and then the lowest y value that's being used below that is starting at negative a quarter. So we're going to have to write our range as y being greater than 0, as well as less than negative a quarter. We know that it's negative a quarter because that came from the reciprocal of negative 4. Negative a quarter and below. So y is less than or equal to negative 1 quarter, where y is a real number. All right? And our horizontal asymptote, we can see, was this line, the x-axis. So the horizontal asymptote at y equals 0. For our final example, we'll look at another parabola, but this time a parabola that has no x-intercepts. X squared plus 1 is a basic parabola shifted 1 unit above the axis. All right, so since it has no x-intercepts, it has no restricted values, the domain would be all real values. There will be no vertical asymptotes. So let's start working with the other properties. When y is 1, reciprocal y is 1. When y is a half, when y is 2, y is a half on both of those points. When y is 5, it's going to be a fifth. Okay? And this is going to approach horizontal asymptote, x-axis. We're going to get a graph something like so. Kind of driving along the road, a little bit of a hill, and then coming back and continuing along, hugging the x-axis. So we have no vertical asymptotes. Our range will range between -1 inclusive and 0 non-inclusive. So y is between 0 and 1. Watch your equal signs on your inequality. Any values of y in that range are valid, and our horizontal asymptote occurs at y equals 0. To conclude, let's just summarize some of the major results we've come to learn about with reciprocal functions. We've taken a polynomial function, f of x, and we've reciprocated it to get 1 over f of x, where of course f of x cannot be 0. At these values of x, where f of x is 0, we have found that there will typically be vertical asymptotes on the reciprocal function. And as we've also seen, many reciprocal functions also end up having horizontal asymptotes. So, the relationship between the y values of the original graph and the y values of the new graph. For a given x value, the x values do not change, but for a given x value, y values on the original function which were greater than 1 end up being between 0 and 1. For example, take a y value of 3, you reciprocal it, you get a y value of a third, a number between 0 and 1. We notice that y values of 1 stayed as y values of 1. Y values between 0 and 1 became larger, greater than 1. Y values of 0, that's where our vertical asymptotes came into play. Y values between -1 and 0 became less than -1. And y values of -1 stayed as y values of -1. And y values less than -1 became y values between 0 and -1. So I like to sum all this up in a few basic things. The values of 1 for y, 1 or -1, stay the same. 1 stay the same. Zeros become vertical asymptotes. Points that are far away from the x-axis, farther than 1, end up becoming between 0 and 1. So points that are far become close, and points that are close, between 0 and 1, become further away from 1, become far. 1 stay the same, zeros become vertical asymptotes, far becomes close, and close becomes far. Hope that helps you in your graphing of reciprocal functions.